great talk.
Thank you.
Paulina, then you can share your screen.
Yeah, thanks.
Yeah, we see that. So our next speaker is Paulina Sowicka. You can go ahead.
Thank you. Today I'm going to tell you a little bit about my favorite stars, the GW Vir stars, and highlight a bit of my research, my PhD research on them. To begin, pulsating stars come in many different flavors, as you can see in this plot, where you have many groups of pulsating stars with different restoring forces, different mechanisms. And we, of course, are interested in the white dwarfs, which are in this shaded area. And if we actually zoom in here, we can see that the white dwarfs also come in many different flavors. And my work is mostly focused on the GW Vir stars. And this instability strip is the first one that is approached by a post-AGB star. Then we have the domains of DB white dwarfs or V777 Hercules stars, or DA white dwarfs, also called ZZ-SETI. The GW Vir stars that I'm interested in span a large range of surface gravities, as you can see, and of course of the effective temperatures as well. Some of these stars are still surrounded by planetary nebulae, as you can also see in this overlaid point. PG1159 stars, this GW Vir instability strip is mostly populated by PG1159 type central stars, but also there are some Wolf-Rayet central stars of carbon sequence. These stars are hydrogen deficient, carbon, oxygen, and helium rich, and the typical composition of these stars I show you here. The main spectral feature that is to distinguish the PG1159 stars is this absorption trough made by the helium 2 lines and adjacent carbon lines. So this feature in here. And what is very interesting is that basically any star has a different composition. So there are very strong variations between this ratio of each element found from star to star. These stars show photometrically detectable variability, which is of low amplitude and have time scales as short as a few minutes. The longest periods we find is about half an hour. So you can see in this marked light curve comparing to the other variable white dwarfs. This variability is mostly due to a kappa mechanism that is associated with the partial ionization of K-shell electrons of carbon and oxygen in the envelopes of these stars. But there is also a theoretically predicted Epsilon mechanism that is connected with the varying nuclear energy generation rate in these stars. And you can see in this picture, along the evolutionary tracks, the regions in black where the Epsilon mechanism could operate, and in red where the kappa mechanism could. And this shaded area shows where is the region where both of these mechanisms can work. And you can see that there are many stars that actually populate that area. Unfortunately, so far there are no observational evidence for this mechanism. These stars are thought to be formed due to a born-again phase, which means that the final thermal pulse of this post-AGB star happens either at the as is shown with this dotted line when in the post-AGB stage, when the hydrogen burning is still active and the star kind of loops back, and the other way is the very late thermal pulse that happens when the star is already on the cooling sequence, on the way to cooling sequence, and the solid line shows this track. What is important is that hydrogen and nitrogen are the trace elements that can help us distinguish between these two formation channels. The most striking characteristic of the GW Virginis instability strip is that it is not pure. In fact, we find that up to 50% stars in this instability strip pulsate, which is on contrary to the other white dwarf domains, where basically all of the stars that are within the instability strip pulsate. This prevents the generalization that we use, that the interiors of these pulsating white dwarfs represent the interiors of all these the white dwarfs, and in this case this is not possible. So that suggests that they might have a different evolutionary history. The existence of both pulsating and non-pulsating stars in the GW Virginis instability strip was indeed a challenge to the theory. The first idea came that there is an observed nitrogen dichotomy, that all nitrogen-rich stars are pulsators, whereas the nitrogen-poor stars are all non-pulsators. Later on, that idea was refuted, and it was put forward that it's helium that is preventing too much helium is preventing the development of the pulsations. Later on, it was found that it's actually the high oxygen and carbon abundance that are responsible for pulsational driving in these stars. Until the most recently, the same stars of the same carbon and oxygen composition and the different nitrogen abundance were studied, and it was kind of proven that the first idea is the correct one, that it was only the nitrogen that distinguished between these stars. Therefore, the part played by nitrogen is really intriguing in this context. However, the one culprit still remained, and that is this star that I'm marking here. That is the only one nitrogen-rich star that has never been shown to pulsate, which was really a big challenge. A number of authors observed that stars, starting from the pioneering work of Grauer in late 80s. Unfortunately, these authors didn't find any variability on the time scales between 60 seconds and 1 to 2 hours. Later on, Schuch and collaborators also observed the star using bigger telescopes and also did not find anything. Unfortunately, these authors didn't mention any detection limits. Later on, Steininger and collaborators observed the star on 4 nights, collecting almost 6 hours of data, and they still did not find anything. What is worth noting here is that the highest noise peaks here were at the limit of 4 millimag. So we included this star in our survey for variability using a 10-meter class telescope, GTC, in a so-called filler program, where we got a bit over 1 hour long light curve, and that is presented in the top panel, where we actually could see a clear variability. This variability was then reflected in the Fourier amplitude spectrum as two pulsating modes, and the fit using these two is shown in orange, just to highlight the variability. So the amplitude of this variability was comparable to the limit of the noise level of the previous observations. So they might have been just hidden in the noise. Unfortunately, this light curve was very short, just 1 hour, and the periods are relatively long for these stars, so that called for confirmation. And after many unsuccessful runs, we finally got a confirmation this year using a 1-meter telescope. And you can see here 5 nights with one night break in between due to bad weather, where you can see that the variability is evident. And on these nightly light curves, the main characteristic is that the amplitudes of this variability is changing from night to night, from one night to the other. So from like 6 millimag in the last night to something about 2-3 in the first. This is a behavior that we actually know and we have seen in many other GW Vir stars, that they tend to change amplitudes and sometimes even frequencies. Sometimes we also see a disappearance of pulsations for a period of time. We then calculated a Fourier transform of the whole run, which is shown in here. In gray, we show a Fourier transform of the comparison star for comparison. And we can see that there are 4 main groups of pulsations, around 40 cycles per day, around 55 cycles per day, 90 and 113. And one thing has to be noted, that actually the higher frequency groups might be combination frequencies of the lower frequency groups, but these confirm the same variations that we already found in this very short light curve. When we plot these frequencies as periods in the diagram, we can see that these variations detected here are within the expected values for GW Vir pulsators. So to sum up, for the time being, there is a clear separation that all nitrogen-rich PG1159 stars are nitrogen-rich, are pulsators, and all nitrogen-poor ones are non-pulsators. This is evidence that the pulsating and non-pulsating PG1159 stars have different evolutionary histories. And it actually seems necessary that a star has to undergo a very late thermal pulse that produces that nitrogen to become a pulsator. And that nitrogen is just a tracer of this evolutionary history. Does it mean that the nitrogen problem is then solved? Well, maybe not so fast, because out of 55 known PG1159 stars, we know only 14 that have nitrogen abundance or its upper limit assessed. So this is a really small number considering the total number of the known stars. And of course, we need more observations, both the spectroscopic observations that allow to determine the abundances, but also the photometric observations that we can use to check the variability of these stars. We are doing both, and this is just a highlight of our survey results with large telescopes, where we actually managed to push this noise limit down to about 3 to 4 millimach for most of the stars, which here are, of course, some outliers, but we can actually see that in here there is a non-pulsator, which was just a test of this method. We have here PG1144, and here we have another possible pulsator that still needs confirmation. So to sum up, we discovered pulsations in PG1144, the only known nitrogen-rich PG1159 star that was never shown to pulsate, and that confirms the link between the nitrogen abundance and pulsations in these stars. We are carrying out a survey for variability among these non-pulsating stars and those that were never checked for variability, providing better detection thresholds for these stars. And of course, we are following up some stars with spectroscopic observations that will be used to derive the abundances. And our goal is to have a first statistically significant sample of these stars that will have information both of their evolutionary history, but also on their variability content and the mechanisms of excitation of pulsations. Thank you for your attention.
Thank you, Paulina. Very nice talk. Nice to see another mystery being solved today.
Yeah.
Do we have any questions? People can either raise their hands or type in the chat. We have one question from Mike Reed in the chat. Thanks, great talk. It seems to me that perhaps the pulsations should have been detected in some previous observations. Could the star just pulsate occasionally?
I think that there might be a few cases. First of all, that the detection thresholds might have been just not enough, but they were not quoted for a few attempts. The other thing is that we see that sometimes there's beating between the closely spaced pulsation modes, and that can also cause the pulsation amplitudes to drop below the detection level. So that could also be a case in there. And these runs that were the first ones, these were really short runs. So that could have been also one of the reasons. So we have a few, at least a few possibilities, and therefore I think that it's really important to reobserve the stars that were not shown to pulsate because of that, because maybe this time it will be possible, maybe this time the amplitudes will be high enough if the stars are pulsators so that we can detect it.
Solan, you have a question? You can
yeah, I do have a question. Just a short question, though it's very linked to the previous question. I was only wondering exactly what happens and these stars actually pulsate on and off and all these changes, and what exactly the mechanism. That's what I sort of thought, and you know, if there is a proper explanation for that, if there isn't any, that's okay. But I was wondering, and that links to the nitrogen abundance, the on and off, they come on and off, and they change these millimagnitude variations and so forth. That's what I was wondering. Thank you.
Yeah, so for the on and off behavior, I don't think we have an explanation yet. There is one case that is really intriguing, and this is K116 that was observed in tests, and that in some test sectors it was found to pulsate, while in the others it didn't show anything. So this is something, if this is really the behavior of the star, then this is really intriguing, and for now we don't have really an explanation for that.
Okay, thanks.
Thank you.
Any more questions? While people are thinking, I have one myself. I suppose not many have been observed by tests in the 2-minute cadence, but can the 10-minute or 30-minute cadence help you?
30-minute for sure not. 10-minute, I think only for those that have really long periods, but if they have 30-minute long period, that would still be a bit difficult. And for these stars, for those that were not discovered to pulsate, or those that were never checked, the main problem is that these are really faint. So the ones discovered by Sloan, in Sloan data, these are mostly like 17th magnitude stars, very blue. So it's really difficult to get good quality data. And as we can see, we really need to have these detection thresholds low if we want to discover more.
Thanks. I think Mike has a follow-up.
I have a question.
Okay, go ahead. Well, I'm trying to make a sense of what I'm reading there.
Hi, nice talk. You have mentioned very large thermal pulse as a way to achieve a high nitrogen-rich abundance, and perhaps as a connection to the source of the pulsations. But is there any relation with the initial mass of the PG1159 star, like for instance being these nitrogen-rich abundance characteristics of the results of hot bottom burning evolution in a massive AGB star, which is also favoring high nitrogen-rich abundance? Do we know the masses of the stars which are nitrogen-rich?
We know masses only from astroseismology. So we know masses of those that are pulsating. And from the top of my head, I don't think that these were really extreme. I think mostly like between 0.5, 0.6 solar mass. So that would be like standard. But I don't remember the exact numbers from the top of my head.
Thank you.
Mike Reed, I see your hand is up, so you can ask your question if you want.
What I was trying to get at is that, is it possible, because these are such hot stars, that there are mixing regions that are moving the nitrogen in and out of the driving region?
So from my understanding, nitrogen in this abundance is not really providing the opacity to have any influence on the driving. That this is really, even in the nitrogen-rich ones, this is a really low nitrogen abundance of like 2%. So I mean, I don't do the model calculations, but I think that it doesn't have any influence.
Any more questions? It doesn't seem so. So thank you again, Paulina. Very
Thank
nice.
you.
I will then stop the recording.